Hello, I'd like to do for you an example problem from my unit on reverberation and architectural acoustics. A main goal of our approach to this topic is to help you find out how to find the reverberation time for a room. Reverberation time is called RT or RT60 very commonly, and that refers to the amount of time it takes in a given room between when a saturated sound, so you turn on a sound and let it fill the space. It's the time between when you shut that off and when the intensity of it is 60 decibels lower. It's a way of formalizing in a measurable way. So for things like a concert hall, it may be in the neighborhood of about 2 seconds. For something like a recording studio or isolation booth, you don't want a lot of reverb in there, so you can add it in post if you want. So for something like that, you want reverb time significantly less than a second. So it's a number of seconds. It's a way of formalizing how much reverberation you have in a room. So there is an equation, thanks to Wallace Sabine, a professor from Harvard about 100 years ago, maybe a little more. Right? That's a way of figuring out what the reverberation time is. And it depends on the frequency of the sound being played and the dimensions of the room and what the materials are. So I'll write out what that equation is, and then we'll do it. And I'll try to change my focus a little bit so everything is readable as I'm reading it. So I'm supposing we're in a room that is 15 by 10 by 12. And we'll say we're playing a 250 hertz sound. We want to see how, you'll see what kind of reverb time we get for this. Delay, my video's stuck and I'm just making sure it's okay. The ceiling is covered in fiberglass. So that has an absorption coefficient of 0.44, and the floor is a hardwood floor. So that has an absorption coefficient of 0.11. Now, what we need to get is the absorption area. So we get that by multiplying the area of the surface by the alpha. Now, I think this one is 15 plus 1.5. That should be 16.5, but I don't want to be wrong. So, okay, 16.5 is that absorption area. Now, this one, I can multiply 15 times 10 times 0.44. That should be 4 times this one, which I believe should be 66. But again, I'll verify. I kind of trust myself, but I like to verify. So 15 times 10, that's the area of the ceiling times the absorption coefficient, and that's 66. So I'm right about that. All right. So let's continue with the other ones. So the front wall is 15 by 12. The area of a 15 by 12 wall is 180. So the front and the back have the same area physically, but remember the back wall is brick. Where was that? The back wall is brick, and so that has a smaller absorption coefficient. The front is one of these other two sides, which is plywood. So that gets an absorption coefficient of 0.22. And let's see, what are the left and the right walls? That's this one and this one. Those are 10 by 12. And so, right, those get an area of 120, but they have different absorption coefficients. The left side, I said, was glass. So, right, the left side is glass. That's an absorption coefficient of 0.25. And the right side is another one of these generic plywood walls. It's 0.22, like this. So I'm multiplying the area by the absorption coefficient. And you notice I'm kind of doing it just one surface at a time, and there's 6 total surfaces. So getting that big picture is a way to really be off. Now, a small way to be off I would have students do is they'd mix up dimensions on the left versus the front or something like this. So you'd swap two of these. That'll change your final answer a tiny amount. There are larger mistakes you can make, but I just want to point out all the possibilities. So we have 180 times 0.22. That's 39.6. 180 times 0.03. I think that'll be 5.4, but let me check that. And then, all right, we have 120 times, I'm just multiplying left to right. That's a quarter of 120, so that's 30. And then, all right, we have 12. 13.2 doubled. I expect this to be 26.4, but I don't trust myself. Okay, good. All right, so what we have is an absorption area for all 6 surfaces. And then the total, we just sum them all up. So this is how it goes. So 66 plus 16.5 plus 39.6 plus 5.4 plus 30 plus 26.4. Let me just to myself make sure I type that in right. So 66 plus 16.5 plus 39.6 plus 5.4 plus 30 plus 26.4 equals 183.9. Okay. Now the units of that, you could write that as square feet. That's dimensionally accurate. You can also call it a Sabin. So Sabin, S-A-B-I-N. It's not spelled like the person's name, but S-A-B-I-N is the unit of absorption area. And that's the total. So what we can say now, oops. Okay, the RT60 there is 0.05 times the volume, just 1800. And you divide by the absorption area, it's 183.9. Let's see what that is. All right, 183.9 is not the surface area of this room, by the way. It's smaller than that because we have to include the absorption properties for this to be meaningful in this calculation. So 0.05 times 1800 divided by 183.9 gives me about, well, 0.49 seconds, let's say. And that's it. So that's the reverb time. That ends that part of it. Now, I'm going to do one little variant on this question too. All right. I believe it's typical in my class. I'll show off, or maybe I think I talked about it at the beginning, or maybe that was a previous draft. I don't know. Things like a church or a concert hall, you're going to want a reverb time more than 1 second, probably closer to 2 seconds. And this is a very, very short reverb time here. So a question I might ask students is, if anything, which of these 6 surfaces is most responsible for this number being problematic? And I hope it's clear which one it is. I mean, you could evaluate which walls are the biggest or something, but I think in this case, the absorption coefficients make more of a difference. And the fiberglass ceiling is the surface that contributes the most to this absorption area. So, so there's a follow-up. If I convert... Hello, I'd like to do for you to plywood. how much does the absorption area change? So the area of the ceiling, what did I say it was? Let me look. 15 by 10. Okay. Okay. Now, I want to know how much the absorption area changes. Now, I multiplied by 0.44 before to get 66, right? If I change that to plywood, see what's the plywood? 0.22. Remember that. So if I change it to 0.22, that cuts the absorption area in half. So 150 times 0.22 is 33. So the change is negative 33 square feet. So I'm losing that many. So the new absorption area total, I mean, I could go through and add the 6 figures again, but what would be better is if I took the 183.9 that I had before and just subtract 33 from it. I don't need anything fancy to do that. It's 150.9 square feet. So just changing one material in the guiltiest surface, right? I get a total absorption area change of it's 33 less. So you take that away, and then the new reverberation time is 0.05 times 1800 over 150.9 now. And let's see what that turns out to be. All right. I get 0.60 seconds. Okay, so by making this change, I changed just one single very absorbent surface to a slightly less absorbent surface, and the reverberation time went up, kind of like we would predict. All right. Now, I didn't turn this room into Carnegie Hall, certainly. The reverb time went up from about half a second to 0.6 seconds. So it's a slight improvement if you want to play music in it. Now, acoustically, what I started as an example is a reasonably small room, and there are some limitations. I mean, I don't think I will turn this into a great concert hall. No matter what I do, maybe like, I don't know, concrete all the walls. I don't know, but it's getting a little bit crazy at this point. I didn't make the reverberation time quality enough to want to compete with the Sydney Opera House, but I did show that we can identify a surface that absorbs a lot versus not, and if you change it, you can change the total absorption area and redo the calculation. So that's the variant on my original example, and I will stop there.